Well, I do have one engineering joke, so we're ready to get to that. So there's a doctor, there's a lawyer, and there's an engineer that are about to be executed by the French with the guillotine. And so they're standing up there. So the first person up is the doctor. They put him in, chop down, and they lower the blade, and it swings down, and it stops immediately about halfway down. The doctor comes out, "It's a miracle. God doesn't want me to die," and so he goes off. The lawyer goes up, and they set it up again. It goes halfway down, stops. The lawyer leaps up. "The law is with me. Justice has been served," and runs away. And then they put the engineer in. Blade's about to drop. The engineer says, "Wait, I think I see the problem." Feel free to use that. All right.
Please pull that down.
So we're going to be, theoretically, we're going to be live streaming as a test. So we'll see how this actually works. I'm not really sure about that. All these new technologies, they confuse and frighten me.
You can go on this stuff. Tim, do you want to?
Tim is not here.
Oh. He should introduce you.
Well, he should.
It's Robin. Robin, do you know where Tim went?
Huh?
Do you know where Tim Weaver went? Oh, okay.
So, well, while we're waiting here for Tim to come back, how many of you have heard of the Turborocket and that particular engine system? Raise your hand. Does anyone not know that? Okay, most people are. Okay. How many went to the lecture last month? Okay, very good.
But some people did not. You need to not present.
Yeah. Yes. Thank you. So just kind of a little backstory while we're waiting here, not officially part of the presentation. So the National Space Society, the Huntsville L5 Society, which is the local chapter of the National Space Society, was kind enough to invite me to present on some of my technical work on a novel pump-fed rocket engine known as the Turborocket Engine. And so I was able to give a presentation on that last month. Thank you all for those that attended. I appreciated that. Tim Weaver was kind enough to videotape that and put it on the Huntsville L5 Society website. And so I have a link to that also on the Turborocket website if you want to watch that videotape. But that has some of the backstory on the background of the Turborocket engine itself. This presentation will be more of a standalone presentation that has some other ideas and includes and the Turborocket is the propulsion part of the propulsion in the title. So that's a little bit of the backstory on that. So anyway, Tim, how are we doing? Let me know when you're ready.
Recording right now.
Well, thank you. I appreciate that. Did you want to? I guess.
Tim, were you going to introduce me?
Did you want to introduce me, or should I just? You don't even have to. I'll introduce myself.
No, I'll do it.
Okay.
Okay.
Sorry, man.
Good evening. I'm Tim Weaver, the current acting president of the Huntsville, Alabama L5 Society, a chapter of the National Space Society. And tonight, we're hosting a talk on home-built space propulsion by John Bossard, PhD.
Thank you very much, Tim. I really appreciate that. And thank you very much for this opportunity to speak to this august society. So as Tim mentioned, my name is John Bossard, and I'll be presenting a presentation tonight entitled Homebuilt Spaceplane Propulsion. So The title perhaps begs the question, and I hope you found it provocative, because it has three rather interesting elements. The first is spaceplanes. So we're going to talk about what is a spaceplane, what is it, how are they different. But then home-built spaceplanes. What in the world? Home-built spaceplanes, the spaceplanes that the home builder can build? Yes. The answer is yes. But then the last part, propulsion. How do we propel these vehicles? And so that will be kind of the subject of the title, the propulsion for these conceptual home-built spaceplane vehicles. So on that, that's kind of the overview of the presentation. But the last bullet is something that I really hope that you maybe will take away from this presentation. And if you take away nothing, I would like it to be something on the last bullet is, why do we even need spaceplanes? Why should we even care? So let's begin with what is a spaceplane. So a spaceplane is a special kind of airplane that can operate within the atmosphere like a normal airplane. It's called an endo-atmospheric. It can also operate outside the atmosphere, exo-atmospherically. And significantly, it can fly through and out of the atmosphere from endo-atmospheric to exo-atmospheric. And we call that transatmospheric vehicle operation. Now, transatmospheric is a term you don't hear as much anymore, though it was popular. It comes around every 10 or 20 years as a popular term. Transatmospheric vehicles is a good term, not as in vogue as much anymore, but still a valid technical term. And I like to say that, in the aerospace community, we've been pro-trans before it was cool to be pro-trans. A spaceplane also, in my definition, takes off and lands like a regular airplane. We call that horizontal takeoff, horizontal landing. It's a FLA, four-letter acronym, HTHL. Not all spaceplanes necessarily have that attribute. Some of them launch vertically. And we'll show some pictures of some of those. But the notion of it taking off like a regular airplane, HTHL, I think is a vital attribute of the spaceplane definition. So bear with me on that as part of my conceptualization of what a spaceplane is. It has all the regular systems of a normal airplane, but it has some additional systems, such as rocket engines, because it's got to be outside the atmosphere. You can't use an air-breathing engine for that. It may need some sort of thermal protection system to protect the system during conditions in which it is exposed to high thermal loading from aerodynamic forces. And so, depending on how you configure the system, we're familiar with TPS systems, like on the shuttle, tiles and stuff that makes the system, protects the spaceplane from these high temperatures that it encounters during aggressive re-entry maneuvers. But not all systems need that depending on how you configure a craft. Dash number 3 is the ballistic coefficient system. Now what I mean by that is a way that you can control the ballistic coefficient of the vehicle, of the spaceplane. And I'll get into that more later in the talk here and explain some of that. But that is an attribute that is not as appreciated, but is nevertheless important. And last, we might have an attitude control system, an ACS system. If you're out of the atmosphere, you don't have conventional aerodynamic surfaces to react to control the roll moments of the system, roll, pitch, and yaw. These are moment parameters, moment dynamics of the vehicle, roll, pitch, and yaw. If you don't have any aerodynamic surfaces like conventional aircraft because you're out in space, then you're going to need some sort of an ACS system. Now this could be a cold gas system, kind of moving you around, controlling your pitch, roll, and yaw. But it could also be an electromagnetic or a torque coupling kind of system. These consist of like rotor wheels that exert torquing forces as you use a motor to accelerate or deaccelerate a wheel. And you can have a wheel on each axis, and by accelerating and deaccelerating those wheels, you can also exert torques to control the ACS system. So those systems require power, but no gas. So good trade-off there between those. And I won't talk a lot more about that system, but nevertheless, once you're out of the atmosphere, you're going to need an ACS system. And perhaps the most important aspect of spaceplanes is that they fly at higher speeds and altitudes compared to conventional airplane, and that's what we like about them, and that's what makes them exciting and interesting. So from a usage standpoint, what are some of the fundamental advantages of spaceplanes for space access? And when I say space access, I mean not just orbital access, but I mean suborbital. Basically, getting up into a exoatmospheric kind of condition, and the broad range of speeds and altitudes that might entail. So in this world, we adjudicate our performance with a parameter known as the delta V, or the delta velocity. This is a standard term that I'm sure most of you all are very familiar with. The delta V is kind of the change in velocity that your vehicle can experience given the performance limitations of the vehicle itself. And it's sort of the coin of the realm for aerospace trajectory analysis. And so the way to think about it is, if you have a vehicle with a given starting mass, the mass initial, and it can poop out mass out the back at a velocity of V sub E, or the exhaust velocity, then by the time you've expelled all of the propellant that you have on board, you will have, at that given exhaust velocity, you will have changed your velocity by delta V, by that amount. So it's just a very simple dynamic equation that applies to rocket vehicles, and it can also, you can roll in terms like drag and gravity to still make this term usable. So it's a very powerful expression. The exhaust velocity can also be shown in terms of the I sub SP, or ISPs, a specific impulse, times a unit conversion term. The ISP can be thought of as sort of the gas mileage of the rocket system. It's like how much thrust you make per pound mass of propellant flow rate you have through the system. Unfortunately, sometimes in the engineering world we cancel out terms, and we sometimes refer to this, the ISP, in terms of seconds. It has 350 seconds of ISP. It's sometimes shorthand for that. And that has led to a lot of confusion because the ISP is not a time term. It's actually force times time divided by mass are the units, or the proper units for that. And so we have an unfortunate shorthand, and we cancel those terms and refer to the second. It's kind of confusing. So, pro tip, always refer to ISP as, in the proper units, force seconds per mass. English units, it would be pound force seconds per pound mass. SI units, it would be Newton seconds per kilogram. So, and then the initial mass, as I mentioned, that's the upper term in there, but I've, got the case wrong there. Mass initial is the propellant you have on board, plus whatever your burnout mass is, which is the mass that you arrive at when you've expelled all your mass. So anyway, so that's a very quick snapshot for the delta V of a flight vehicle. And we use that, and it applies to any vehicle that you're trying to accelerate to suborbital or orbital velocities. And so the parameters there, you can kind of see that if you have a lot of mass that you start with, or a lot of propellant mass, and or you have a high ISP, then you can achieve a high delta V, and that's what we're kind of going for in our vehicles, as much as we can. So let's move on to bullet number 2. Now this might be a little controversial, a little enigmatic, but it's a claim that I make, and I want to walk you through that so that you'll appreciate what I'm trying to say here. When you put wings on a rocket-powered vehicle, you actually, in essence, become an air-breathing propulsion system. Now that seems a little crazy. How does that work? Well, it works because when you have rocket thrust and you have a winged vehicle, you're generating lift through the vehicle as it flies through the air, as it's propelled by the rocket thrust. And so, in essence, the wings of the vehicle are converting some of the momentum of the rocket thrust into downwash from the air, and that's producing a thrust, a lift thrust in this case. So, it's relatively efficiently, because as we know, in a vehicle that's at steady state velocity, the lift to drag ratio of the vehicle is equal to 1 over the thrust to weight rate of the vehicle, right? So that's where you can see where if you have a high lift to drag on a typical vehicle, then you can convert that thrust efficiently into a lift component. And so another way to kind of visualize it is like this. Imagine you have a rocket-powered airplane. It's got a little rocket, it's got wings on it. And now you have an identical one, but it's pointing in the opposite direction. Okay, so one's flying north, one's flying south. And then you put a beam between those two, and then you turn them on, and now they're spinning around. So they're kind of a rocket-powered wing. Is everyone tracking my visualization here? Well, what's going to happen to that thing? Well, it's going to be like a helicopter, right? And it's going to helicopter up. And so that's in essence, so now you're generating air-breathing propulsion. You're reacting air mass down from the rocket-powered fan. So in essence, now that's an example where we have kind of two rocket planes and a kind of a finite radius. But a vehicle, a rocket-powered airplane, spaceplane on an ascent trajectory can kind of be thought of as one of these fan things, but with an infinite radius of boom, if you will. So anyway, I hope you'll keep that in mind and ponder that in your spare time.
So are you just trying to be clever with that?
No, I'm not, because and I'll tell you why. Because my definition of air-breathing propulsion is I try to make it a little bit more broad. And in my definition of air-breathing propulsion, it is using the ambient atmosphere or ambient fluid to create forces on your flight vehicle. And that can be any type of forces. It can be lift forces through a wing, or it can be deacceleration forces through a heat shield. Now, we don't normally think of a heat shield as being air-breathing propulsion, but in the strictest definition of exchange of momentum and generating forces on an aerodynamic vehicle, a heat shield is an air-breathing propulsion system. So anyway, I leave that to your cogitation. Okay, moving right on along. So what this translates to for spaceplanes is that the logistical simplicity of these vehicles, if we could achieve these high delta Vs in a single stage with no staging, that translates into increased reliability and safety. And so that's another positive attribute of spaceplanes. And so, when you have by comparison in our conventional launch vehicle system, you have a multi-stage rocket that takes off vertically, climbs out, drops off stages, and flies out into orbit, it experiences a lot of, technically challenging things that have to happen to it, not the least of which is the staging process. And staging is a very sketchy process in a launch vehicle system. It is one of the highest failure probability issues for launch vehicles, the staging. You have all sorts of things that can go wrong, the staging doesn't work, the actuation mechanisms get jacked up, things don't separate cleanly, you have recontact. So it's practically a proverb that staging is a technical issue, and launch vehicle providers go to a great deal of effort to try to iron out all the kinks there, and it's still not perfect. So if you don't have to stage, you kind of eliminate that problem. Next, horizontal takeoff, horizontal landing. The horizontal payload integration is easier, safer, and less expensive, I claim. Especially for payloads that want to be horizontal initially. Meat payloads, i.e. people, are a classic example of that. And I claim that they prefer horizontal integration, despite the fact that you may think it might be neat to climb into a spaceship and then lean back in the seat and then launch that way, as opposed to a normal aircraft kind of entry in which you walk in and sit down in the seat. And if you don't think that's true, I can assure you, if you've ever tried to get in a vertical launch seat wearing a dress or a kilt, you will definitely prefer horizontal integration. Lastly, I claim that the lower ballistic coefficient, because we have these large aerodynamic surfaces, wings and whatnot, can be a substantial way to reduce re-entry aerothermal loads because of the lower ballistic coefficient of a vehicle like that. We'll talk about that a little bit more. Now, unfortunately, the last bullet did not show up on the screen, so I don't have a way to show that.
Tell us what it says.
But the last bullet says, and this is again probably something that you might find controversial, I claim in the limit, space planes will yield the lowest dollars per pound per delta V for space access. And that is, that's not my opinion, that's math. We can walk you through the math on that. If you have a winged vehicle, especially with air-breathing propulsion, you're going to be cheaper in the long run than a vertically launched, staged launch vehicle in terms of dollars per pound orbit. And there's a lot of that statement is freighted with a lot of assumptions, but I urge you to consider that deeply because it's true. I'll take a quick question. I normally don't take questions during my talk, but if it's fast, I'll take one.
do we have sufficient ISP to launch with a single stage now?
For vertical launch or horizontal takeoff, horizontal landing? Or the space plane kind of thing, is that what you're talking about? That has not been shown, but the theoretical indications show that that's clearly possible. And I'm going to show you some space planes that, for many developers, that believe it to the tune that they're willing to invest tens or hundreds of millions of dollars in developing those vehicles. But I think it is a good point to bring up. At this point, a horizontal takeoff, horizontal landing vehicle taking off with no staging and achieving orbital velocity has not been demonstrated. Some people say it's impossible. Those people are wrong. Okay. So, space planes. Let's look at a few examples of some space planes, and some of these are familiar to you, some of them are going to be less familiar. Actual space planes I group into the space shuttle, our 30-year friend. Another one is Dream Chaser. I might be familiar with that, being developed by Sierra Nevada Space Systems. Small kind of mini shuttle, if you will. X-37, kind of a classified Air Force vehicle. And then, of course, the legendary SpaceShipOne and now SpaceShipOne vehicles. These are actual ones that have been built, flown, go into space, come back now. So we also have a number of legacy systems that were proposed but never built, most notably the NASP, the National Aerospace System. How many of you all worked on NASP sometime in your career? Anyone? Anyone? Okay. John, did you ever work on that? I think you did.
I worked near it.
Okay. You were NASP adjacent. So.
I worked on X-37.
Exactly. Did you ever work on NASP? Kind of NASP thing? Another one was X-33. It was kind of a suborbital vehicle. That was came out of that kind of the 90s. We'll look at that. That was another system that had a lot of stuff that was more than proposed. It was built, but it never flew. And then third dash, there's Star Raker. That was a concept from the 70s and 80s. How many of you have heard of Star Raker? Okay, I'm gonna go into that. John, we've talked extensively on that. So anyway, I'll show you some pictures of that. Skyline. Skyline was a British system, again, horizontal takeoff, horizontal landing, classic orbital vehicle, proposed.
Alan Bond.
What's that?
Alan Bond.
Alan Bond, yeah. Bond, Alan Bond.
The name's Bond.
Yeah. So a very interesting system. Hotal was an originator of Skyline. We'll show some of that. Now we have a number of new space systems, new space companies that are doing things. Destinus is a Swiss-based company developing a kind of a high-speed plane, can kind of go extra-atmospheric combined cycle engines. Show some pictures of that. Venus is a company down in Texas developing some combined cycle interesting vehicle systems. Radiant Aerospace, very interesting. They are going for the holy grail, rocket-powered horizontal takeoff, horizontal landing. All rocket, single stage to orbit vehicle, very ambitious system, very interesting. And then Atrex is another interesting company that is developing some novel spaceplane concepts using some very interesting propulsion technology. And we'll talk about that in a bit. I'll show some of the pictures of that in just a minute. So those are our kind of snapshot of some of the space planes. A few pictures here. The space shuttle. I never loved the shuttle more than until SLS launched. And so I then came to appreciate the amazing, what an amazing system that was. But it was too late, come and gone. But amazing system, 30 years of operation, 130-ish flights, big throw weight to orbit, 55,000 pounds, vertical takeoff, horizontal landing. Liquid rocket engines with solid rocket motors, probably the worst combination of propulsion for a launch vehicle. To combine, it's kind of the superposition of the worst choices of all these systems. Solid rockets are a real challenge, and I think they're not a good choice for that, and von Braun would be rolling over in his grave when the solids got strapped on the thing. Just my opinion. but an amazing vehicle, lands like a space plane. Okay, Dream Chaser, currently developed by Sierra Space Systems. It's boosted on a main vehicle, vertical takeoff, horizontal landing, a couple of stages to get into orbit. Vehicle that's put in orbit that's I think around 12,000 pounds, and it has some good fraction of that is payload that you would have. It can bring back about up to 4,000 pounds, so kind of an interesting vehicle. And lands on a runway, front skid. Huntsville International Airport has been cleared to do landings of this vehicle, so they're looking at this as a possible return site for the Dream Chaser, which would be very.
John, was that one derived from the HL-20, the Langley HL-20?
It could well have been. That had a lot of predecessor lifting body work. That one and maybe some others. I'm not quite sure on all of its history on that.
What is the booster it's using to get that up in orbit?
Well, it's designed to be boosted by a number of vehicles. The baseline vehicle is the Atlas V, but it could go on other vehicles. It could go on a SpaceX Falcon 9. It could go on a Delta. It could probably go on a Vulcan. Could probably go on one of the Airventure 5. So it can fly on multiple systems, but its baseline is Atlas V. X-37, interesting vehicle, kind of a black program. Again, much like the Dream Chaser, vertical launch, a couple of stages of orbit. Don't know the burnout mass, don't know the payload mass. Talk to Mr. London. He can tell you all about it prior to him having a kid.
This changed quite a bit from its inception.
Yes. Another one, and this is a significant one, which is SpaceShipOne. Now this is as you all, I presume you know, but I'm going to go through it anyway. So it uses a carrier aircraft called the White Knight 1. That's the gangly kind of thing with two afterburning J-85 turbojets on the top. SpaceShipOne is carried underneath. It climbs up to about 50,000 feet. The SpaceShipOne drops off, and its hybrid rocket motor lights and carries it on up to above 100 kilometers. That's called the von Karman line, by the way. 100 kilometers is kind of not only considered kind of the edge of space. U.S. is a little bit different. I think they sometimes adjudicate it at 100 miles. But in any case, this could make some, flew on some amazing trips. Its first flight was in the summer of 2004. And it did that first flight and then came back down. It achieves about 3,000 feet a second total delta V, if you want to look at it from the delta V equation. It weighs about 2,000 pounds and can carry 3 people. I had the privilege of getting a chance to work a little bit on that system. And this is an important vehicle for me personally in my talk here because I see this vehicle as sort of the existence proof for home-built spaceplanes. And I'll tell you why its emergence is true to that notion. Okay, let's look at some legacy spaceplane systems. The National Aerospace Systems was a very ambitious system starting in the 80s, probably in the 70s through the 80s, before finally collapsing under its own bureaucratic gravitational implosion. It became such a bureaucratic black hole that it just couldn't sustain itself. At one point, the project office, consisting of all civil servants to run this program, not the contractors, just the NASA program office had over 120 people in it. And that does not include all of the people at the propulsion and the aerospace vehicles, in which there were multiple. So it was really unfortunate because it had a lot of good ideas, but it just could not overcome its bureaucratic entanglements. The vehicle could horizontally take off, horizontally land. It was slated to be single-stage orbit, and initial concepts used scramjet engines, which are a high-speed air-breathing engine, supersonic combustion ramjet engines. That's what that kind of stands for, and considered to be operating at very high speeds. And it never achieved that. The technical hurdles were too much, but it was a very interesting concept, and a lot of dreams got crushed, when this program went away. And a lot of us young engineers, I was a young engineer working at Airventure at the time and was looking at this, and I was very excited about it. But then I saw what I thought were some issues, and I started stepping away from it and realizing I don't know if this program's actually gonna make it. And so I felt like I was the last guy to leave the apartment as it collapsed in on itself. And many of my colleagues and friends did not escape the collapse of the system. And I feel like they were scarred from spaceplane technology and the notion of single-stage orbit vehicles from that experience in the collapse of NASA. That's a conjecture. We'll only hear it here. Another legacy spaceplane system, X-33, contracts awarded in 1996. There were a number of interesting concepts. This was the winning concept by Lockheed Martin. Did I get that right? Lockheed Martin. I call it the Stay Puft Dorito, but basically it was a large lifting body, vertical takeoff, vertical landing, linear aerospace, special type of rocket engine on the back. Systems were tested. This was going to be a suborbital test bed, and the Venture Star follow-on program was going to be the suborbital bigger vehicle. Built some test articles, built a lot of the linear aerospace technologies. The linear aerospace engine for this system is actually out on the NASA rocket garden. If you ever want to see that, you can go out to building 4205 and see in the rocket garden the linear aerospace from this system that was developed and tested there. Another interesting system, but again, you know, kind of a bridge too far, and through some technical failures, did not survive and was never flown. So let's look at some of these legacy spaceplane systems from previous to that. One of the most amazing has to be the Star Raker program, the Star Raker aircraft. And so you can see the concept of this vehicle and how big it was compared to a 747, an enormous vehicle. It had 10 engines across the back. This was developed in the 1970s and early 80s during the oil crisis. And the thinking was that we need a low-cost access to space that can carry hundreds of thousands of tons of these space power satellites up into orbit and get them set up in there. We need a low-cost way to get those up there. So let's have a system that will do that. And so this was the system that they came up with. It was an interesting conceptual design study. The system actually what we call closed, meaning that the design based on the performance that they understood and predicted meant that the system could actually achieve the payload and the delta V that they believed it could actually achieve. Interestingly enough, the system used turbine-based combined cycle engines, TBCC engines, plus rockets for the system rather than scramjets. A very ambitious program, very cool aircraft, but again, never got off the drawing board. The British also were developing and have continued to develop various spaceplane concepts. The most recent incarnation is the so-called SkyLine vehicle. They're still working on that. Again, horizontal takeoff, horizontal landing, single stage to orbit. It used a novel engine that they now call the Sabre engines, or synergistic air-breathing rocket engines. Basically, it's a combined cycle engine that had rocket-type parts and air-breathing parts, and it could take off as an air breather and obtain the high ISPs of an air-breathing engine system before transitioning to a rocket engine to make it to orbit. Again, the design closed. British engineers are some of the best in the world, and they believe that the system could work. The company developing this is Reaction Engines. They're based in the UK, but they have a facility in Colorado where they're developing some of the engines on that. I wish them luck. It's been a long road. They're making progress. I don't know if they're going to kind of get there, but it's a very interesting concept, and it could be worked out with enough money. Okay, let's look at some of the new proposed spaceplanes that are coming along that I mentioned. Destinus in the lower right-hand corner. That used some novel combined cycle engines with some unique hydrogen-cooled kind of concepts. High-speed, point-to-point and cargo delivery is their idea. Venus Aerospace, another kind of concept out of Texas. They're developing some novel combined cycle engines. They're using rotating detonation engines as their baseline high-performance rocket engine. We'll see where that goes. They're well-funded, as is Destinus. Radiant Aerospace is another company. They have a rocket-powered horizontal takeoff, horizontal landing vehicle, as shown here. Takes off from a runway, all rocket-powered, gets into orbit, and then comes back down and lands. very aggressive, very ambitious program. The propellant fractions on these rocket-powered vehicles are extraordinarily high, meaning that so much of your vehicle has to be propellant to make it to orbit that it's tricky to make the design close. They claim that they're getting close, but they've certainly been able to raise a lot of funding. And up in the upper right-hand corner, we have the Atrex vehicle. This is a spaceplane concept being developed right here in Huntsville, Alabama. And in fact, the chief, the CEO is right here with us, Mr. John Bergmans. John is the CEO of Atrex. And if you are interested in investing in the Atrex, you should talk to John, and he will help you find a suitable investment on the Atrex system. The Atrex system uses a propulsion system that John and I have worked on for decades, known as the ATR engine, or Turborocket, or Turbojet engine, combined cycle engine system that has a lot of promise. And so we wish John all the best on that. And hey, the best is yet to come. In thrust we trust. Okay. Now the problem with most of these space planes, not Atrex, sorry, John. The problem with most of these spaceplane concepts is that they're big. And that means they're expensive. And that means they're expensive to develop. And they require government-sized programs and investments. And so they're just going to suffer the same risk. They suffer the same fate, or risk suffering the same fate that NASC and all these other programs have, that they just so big that they can't be done. And so that's a problem when you make them that big and try to be that ambitious on them. So let's ask a different question. What is the smallest possible spaceplane? What is the minimum viable product for a spaceplane? What's the minimum number of people? What if we don't worry about what our achievable delta V is on the system, but let that come out as a output variable from our design? What is the minimum requirements list that we need to get one of these planes going? What is the spaceplane MVP, minimum viable product? My claim that spaceplane MVP is the home-built spaceplane. So you might ask your question, I mean, for some people, home-built spaceplane is almost an oxymoron. How can you, spaceplanes are so hard and expensive and big and difficult, you're going to build a home-built one. No, that doesn't sound viable. So is it even possible? Well, in 1999, I was very interested in this question, and I started putting together a presentation that I presented at the 1999 Airventure, Experimental Aircraft Association's Oshkosh. If you've heard of that big gathering of experimental aircraft enthusiasts, these are people that are enthusiastic about all kinds of aircraft, and they build their own airplanes. It's an incredible event. If you're not familiar with the EAA, I encourage you to look into that. It's really amazing what they're able to do. And my argument there was to encourage that argument, or to make that argument, that home-built spaceplanes are not only possible, but they're quite possible and interesting. And that was given in the presentation there. You can still find copies of that presentation online if you want to find it. The idea basically was that if you take the experimental aircraft guys, the EAA guys, and you take the experimental rocketry guys, which there's a big group of that, and some of us are here, the intersection of those two enthusiast groups could build a rocket-powered airplane. That is the essence of the minimum viable project spaceplane. And when I gave that presentation, remember this is 1999, SpaceX wasn't around, SpaceShipOne was a gleam in Burt Rutan's eye, Blue Origin wasn't around, none of these companies were around, and they were just starting to get started. And so I feel like what happened with Burt Rutan and Scale Composites and building the SpaceShipOne, it was exactly that conjecture that put that spaceplane together. It was the intersection of the experimental aircraft people, as given by Burt Rutan and Scale Aircraft, one of the preeminent aircraft builders, and it was the experimental rocketry guys embodied by our very own Tim Pickens here in town. And most of us know Tim Pickens, who was doing hybrid rocket development and pitched the idea of hybrid rockets to Burt Rutan. It was that union of the experimental rocketry guys and the experimental airplane guys that put that together and made that real. And so that prognostication out of that, my humble presentation, kind of came true. I can't honestly claim that, my presentation was the one that put it over the finish line. That would be pretty obnoxious to make that claim. Though, my friend Dan, who worked for Berkeley at the time, gave this chart presentation, this 1990 presentation to Berkeley, and he saw it and liked it. And so I like to think that even if it didn't, solve a lot of his problems, at least it made him feel like he was doing something that people cared about. So that synergy, all of that to say that SpaceShipOne is the existence proof that home-built space planes are not only possible, but we've flown them. And we did that nearly 20 years ago. This is one of the few slides from that presentation. It's just a cartoon showing what a representative home-built space plane might look like. It looks pretty similar to what SpaceShipOne and representative space planes look like. Just a simple vehicle, has wings, it has empennage and control surfaces. The volume inside is dominated by the propellant tanks, because if you want to get halfway decent delta V, you've got to carry a lot of propellant. So that's one of the characteristics of these vehicles. It may have some sort of life support system, may have thermal protection system for the crew, and it may have some sort of crew or recovery system for it. We don't see that a lot. We like to have the pilots stay with the aircraft to the extent possible, though one of the pilots did bail out of the Spaceship Two when it had its failure or had a problem a number of years ago. He was the surviving pilot from that. So we don't go into the crew recovery as much, but it's still a good thing to have in this picture. Okay, a couple of general characteristics about home-built space planes. And this is kind of a useful slide because I think kind of in a thumbnail cover some of the things that are going to be different from a home-built space plane versus a home-built aircraft. The first is that you're going to have large propellant fractions. A typical airplane might carry 20% of the gross takeoff weight of the aircraft might be propellant. Dave, you're building an RV-8. What is how many pounds of propellant do you take off with on a full load about?
360 pounds.
360 pounds. And what is the gross takeoff weight of your aircraft? Full passengers, full fuel.
1,800.
So 3 over 18 is a good fraction of what you would get. That's pretty good. RV-8 is a good plane. But in a space plane, it's going to be much higher than that. It'll be above 50%. It may be approaching 80%. By way of comparison, the Voyager around the world aircraft had a propellant fraction of above 85%. So of its gross takeoff weight, 85% was propellant. That was a really sketchy getting off the ground, but that's how much fuel you needed for that single-stage orbit vehicle. Another aspect is the propulsion systems are going to be very high performance. They're going to be rocket engines, and I hope combined cycle engines, which combine rocket engines and air-breathing engines. There's an example of that sitting on the table. We'll talk about that in a little bit. The home-built space planes will also need additional systems that we've talked about. They'll need an attitude control systems, ACS, cold gas thrusters, or a torquing system. They'll need systems to cover their re-entry systems. These are thermal protection systems. And also possibly a way to modify the ballistic coefficient of the vehicle, which I talked about and I'll explain in the next chart. And also environmental control and life support system, an ECLIS system, oxygen, and temperature controls for the pilot. Sometimes the ECLIS system is nothing more than a space suit. Sometimes it's a pressurized cabin. And of course, these vehicles will operate at much higher altitudes and velocities than a conventional airplane. Now, I talked about the ballistic coefficient. We're going to do a little math here, so hang tight with me here. The ballistic coefficient is a term that describes the ballistic characteristics of a vehicle. It's simply defined as the mass divided by the drag coefficient times some reference area. And so if you're a shooter, if you're a reloader, if you like guns, you're probably familiar with the ballistic coefficient for your bullets. The ballistic coefficient means that it's inversely proportional to the negative acceleration. What I mean by that is if you have a very high ballistic coefficient like a bullet has a high ballistic coefficient. It has, for its given mass, it has low drag and a low reference area. That means that it doesn't deaccelerate as it's flying along. It penetrates through the air and targets. Contrast that to a butterfly, which has, for its mass, it has a very high drag and a very high reference area. And so it's very fluttery, and so it doesn't, so when it's flying along and it hits something, it doesn't penetrate very well. So its ballistic coefficient is low. For aircraft vehicles, low ballistic coefficients, it's good because it means that the drag is high. So if you have high drag, that results from a low ballistic coefficient, and that reduces your aerothermodynamic loads on it. So, and in fact, if your ballistic coefficient is low enough, you can re-enter from orbital velocities with no thermal protection system, 0. That means, imagine if you're a leaf and you're at orbital velocity, and you're at low enough altitude, so you're starting to, get a little bit of aerodynamic drag. There's a little bit even up at 100 miles. You can re-enter leaves without burning them up. And there are numbers of concepts for some vehicles that have very low ballistic coefficients, and they have no re-entry protection. They have no TPS system. They just flutter in. So kind of a cool idea. The Skylon vehicle utilized that principle because they use hydrogen as the fuel. They had big tanks. It was a big fluffy vehicle, but the ballistic coefficient of the Skylon was low enough so that they needed no fancy thermal protection system. They used traditional refractory metals. They just used high nickel and some stainless steel. And their ballistic coefficient was low enough so that that was more than sufficient to keep them from burning up from orbital velocities. So that's why that's really important. In the lower right-hand corner, you'll see SpaceShipOne that has that feathering mechanism, the tail that kind of folds up. That is a way to create a reduction in ballistic coefficient in SpaceShipOne, and why its thermal protection system is pretty much negligible. It flies at a maximum speed of about Mach 3. That's about as fast as SpaceShipOne gets, and I think Spaceship 2 is similar. And so it doesn't need a lot of thermal protection system. It does a little warm on the nose, but that feathering system helps keep the ballistic coefficient low and the aerothermodynamics low as well. And the right-hand picture is just some concepts that I put together that use a different kind of concept. They use a streamer that comes out of the back of the vehicle. And the streamer, if you've ever launched model rockets, who's launched model rockets? And you use the streamer instead of the parachutes. The streamers, when I was a kid, I always thought the parachutes were kind of cooler, but the streamers are kind of better because you don't get your vehicle lost in the trees as often. It comes down a little easier, a little straighter, and more gently. So you can use those streamers for vehicles too. And with a streamer, you can stretch out the streamer to create an AREF, a reference area, arbitrarily long, so that you can make an arbitrarily low ballistic coefficient. So you have a vehicle, like a Homebuilt Spaceplane, you reel out the streamer, it might be 300 meters long, and gives you a low ballistic coefficient. You come in, easy peasy, and Bob's your uncle. We land on the runway, reel back in, and there you go. Okay, propulsion options. This is another chart that came from the predecessor organization, my predecessor presentation. And I just tried to summarize in a little kind of a chart here some of the propulsion options: solid rockets, hybrid rockets, liquid rockets, and then combined cycle engines across metrics of safety, cost, performance, and availability. Red is like, yeah, it's not so good. Green is, yeah, that's good. And then yellow is kind of maybe better with maybe can be improved with follow-on development. And what we see here is solid rockets. They're expensive. They're not that safe, but they're available. Hybrid rockets, they're pretty safe. The performance is meh, and they're not that cheap, we found out. Liquid rockets, their performance could be improved. It's kind of a baseline. It's kind of what we're kind of thinking about. They're available. And hopefully the Turborocket engine that I'm going to talk about in just a minute will help make that more feasible. And then lastly, combined cycle engines that are kind of the union of rockets and air-breathing engines. Can be safe, they can be low cost, they have great performance. They're not quite ready for prime time. We're working on that, and hopefully we'll have those ready for your Homebuilt Spaceplane project by the time you're ready to fly. Okay, so based on that, the propulsion is the enabling technology for these Homebuilt Spaceplanes. And that's why the propulsion was the last word in my title here, because If you can get a decent propulsion system, then maybe you can get a home-built spaceplane to have some halfway decent performance. And that's what I hope you'll take away from this conversation in our presentation today as well, is that the emerging propulsion options that I'm going to talk about, and the Turborocket in particular, may be the enabling technology for that, and may allow these home-built spaceplanes to be realized. Pressure-fed rocket systems that don't have a pump just don't have sufficient performance. The tanks are too heavy, so you just can't get a high enough delta V from these systems. I mean, you can run them, and the SpaceShipOne was all pressure-fed and had no pumps. But you can see the kind of the delta V's that you're able to achieve on that, and they're not as high as we might want to achieve. And lastly, if we can make realistic combined cycle engine systems, those home-built spaceplane systems may have great performance, really great performance. I propose that the Turborocket engine is the propulsion solution for these kind of systems. The Turborocket is a small integrated pump-fed rocket engine system, sometimes known as a rotary rocket engine. These systems, because of misapprehensions on how they work, have been relegated to the dustbin of suboptimal technology. But I think because the operation of these systems has been misapprehended, the potential of these types of engines has failed to be realized. And so I'm hoping to change that with my development of the Turborocket engine system. They're relatively simple, they're inexpensive, they're safe because they're not pressure fed, and they also, because of their unique geometry, can be combined with other propulsion systems like turbojets to make these unique combined cycle engines. Lastly, the Turborocket engine is open source. The technology is open source. Anyone that wants to develop this has a good idea and a childlike sense of wonder can develop these kinds of systems. So what is the Turborocket system? Well, if you'd come last week, you'd hear the whole story on it. But if you didn't hear that, then I'll tell you that a Turborocket is a pump-fed rocket engine in which the rocket chamber, the nozzles, the effective turbine of the system, and the pump, the parts that function as a pump, all rotate together as an integrated assembly. So it's an integrated pump-fed rocket engine. The engine is fully throttleable, and in other words, you can run the thrust up and down. It can function as a bipropellant rocket, meaning a liquid oxidizer and a liquid fuel, or as a monopropellant, if you only have one propellant that operates as the propellant for the system. And as I said, because of its unique and simple characteristics, it can be integrated with other air-breathing engines to create these novel combined cycle engines. One of these is the so-called RTR engine, which I'll talk about momentarily. So here's a little schematic of the Turborocket engine. The blue is the static elements, the gray are the rotating elements. We can imagine a fuel and oxidizer coming into the system on the left-hand side, flowing axially downward, and then turning radially outward to flow into a combustion chamber where the propellants mix and burn to produce a hot, high-pressure gas that exits from the nozzles of the system. Now the nozzles, as you can see in this view on the bottom, are at an angle relative to the axis of rotation. So the tangential component of the jet velocity imparts a rotation to the Turborocket system, and this is the source of the power that centrifugally accelerates the propellant into the combustion chamber. It's the pump element. It's the pump and the turbine. And so that's why you can get these high chamber pressures from the Turborocket, because it is the tangential component of the jet velocity exiting from the rotor head that provides the power to pump the propellants into the chamber. But that's not the only component of the jet velocity. There's also the axial component. The axial component is the source of the reaction velocity that gives us our axial thrust, and that's kind of what we're after. So that's how a Turborocket engine works in this cartoon. Okay, so because of that simple geometry, it's round, it's simple, it can be integrated into other systems to create these combined cycle engines. Now we group combined cycle engines into two major groups. One is a turbine-based combined cycle engines. TDCC, these have like, these might have like pumps or like fan blades, those are TDCC engines, or rocket-based combined cycle engines, RBCC engines. This would be a Turborocket engine integrated into, say, a ramjet or scramjet, no moving parts, or a rocket in a tube, a ducted rocket as it's called. So those are the kind of two groups. The RTR is a turbine-based combined cycle engine, and there are other variants of that. I'll show you some other concepts, including a fan-based Turborocket engine system which is kind of the model shown on the table. That has a little fan that can be integrated with the turborocket to produce one of these combined cycle engine performance attributes. Okay, getting back to the RTR engine. So the three-letter acronym there, RTR, the R stands for RTR, and the TR stands for turborocket. So it's the RTR turborocket engine. There's a long, sorry story about why R stands for RTR and the recursive nature of the acronym. I apologize for that. But the basic idea is that we integrate a turborocket into the aft end of a basic standard turbojet engine. And it fits within the turbine hub diameter of a standard turbojet engine. And if you do that, now you have the attributes of a turbojet engine, an air-breathing engine with high performance in terms of specific impulse, take off, fly around. But then you have the turborocket engine, a pump-fed rocket engine, for your extra-atmospheric and acceleration missions. But there's a unique synergy that occurs with the turborocket integrated with the turbine, with the turbojet engine, and that is this. In addition to making thrust, the turborocket engine is also capable of making shaft power. And so that shaft power can be used to turn the compressor on this kind of system. And when you do that, and you take the power from the turborocket instead of the turbine in the system, it enables a new mode of operation that we call the air turborocket mode. And basically, the turborocket engine supplying shaft power to the compressor, that air blows back into the afterburner region, and the fuel effluent from the turborocket mixes and burns, like a standard afterburner, to make thrust. That's an air-breathing engine. And this is an air turborocket mode. And I'll show you the cartoon and let you ponder that on how that system kind of worked. But this was the initial system that I thought had a lot of promise. And the RTR engine is, I think, one of the unique and possibly high-performance turbine-based combined cycle engines that utilizes the turborocket engine. Here's a picture of a prototype that I built. This is a small RTR engine. It uses a small RC scale turbojet engine that's about the size of two cantaloupes. And then it has a small turborocket engine in the back of that. You can see it on the far right-hand side. It's pointing to the turborocket engine integrated into it. The turborocket engine was very small. It was about 1.25 inches in diameter. So I hot-fire tested this engine system and was able to show some of the functionality of the system. The performance wasn't super high, but I still think it was pretty amazing to get this far. Here was an honest-to-goodness turbine-based combined cycle engine that combined an actual running turbojet and an actual pump-fed rocket engine that had been hot-fire tested that you could hold in your hand. And I defy anyone to show me another engine that you can do like that, a turbine-based combined cycle engine that you could hold in your hand and that had been tested. Okay, so RTR engine anticipated performance. So here's the chart that shows the specific impulse as a function of the flight velocity. There's a kind of lot of stuff on here to unpack, so I won't bore down into this in significant detail. But your takeaway from this chart is that dotted line shows the possible engine performance that you could get out of the out of the RTR engine as you're flying on some nominal flight trajectory. You're taking off from the runway, you're flying up through the air, you're going faster, you're going higher. And as you go through this flight regime, a flight trajectory, the RTR engine would deliver these kinds of ISP performances as it transitions from a turbojet operating region in yellow through an air turborocket engine operating mode, and then before transitioning to a turborocket engine operating mode. And so that's the kind of the ISP performance that you could reasonably expect from the RTR engine. And if you know anything about ISP performance on combined cycle engines and rocket engines, if you could achieve something like this, it would be extraordinary. And the delta V's that you could achieve with a vehicle with this effective ISP over a trajectory would be extraordinary. Okay. Last picture, here's kind of the cartoon version of this fan-integrated turborocket engine. Basically, you have your basic turborocket engine. The nozzles are shown here on the left-hand side, left-hand end of the system. But it has a mechanically coupled fan that could be a high-performance fan, and because the turborocket can generate shaft power, you can turn that fan and operate both as a combined cycle engine, as an air breather, and then as you transition out of the atmosphere, you can decouple the fan and operate as a pump-fed rocket engine. So, very simple system. This is probably the simplest incarnation of a turborocket engine-based combined cycle engine. Okay, we're almost we're getting close to the end here, folks. So I'll summarize a few things, and then we'll move on to some conceptual spaceplane vehicles. So just in summary, the RTR is a novel combined cycle engine utilizing the turborocket engine. And if you can utilize these systems, you can integrate these into existing airframes and vehicle systems, possibly to create these home-built spaceplane systems. The turborocket and RTR engine development is underway with my little company, BSRD. We've got some analytic models and some design and hardware. We're doing hot fire testing at patent issued on the RTR. Not the turborocket, that's open source, but the RTR has a patent that was issued a few years ago. Okay. Example of home-built spaceplanes. That's kind of what I hope drew you to the presentation here. And so let's look at a few conceptual home-built spaceplane examples, in which we synergize the experimental aircraft guys and the experimental engine builder guys. Obviously, SpaceShipOne is kind of existence proof, and so that shows kind of the bounding circumstances for these kinds of systems and how we can integrate a turborocket engine into existing turbojet engines and utilize that for these spaceplane concepts. Okay, let's look at a generic spaceplane concept. So here's an interesting vehicle. Raise your hand if you know what aircraft this is. What aircraft is this, Dave?
It's the Kinrand, I forget what the designation is.
It is it is the subsonics flight vehicle. This is a little jet-powered airplane, one of the smallest ones. It's available as a kit. You can buy the kit for about $60K. You can buy the engine for it for about another $50K. So for under $150K, you can have your own little high-performance jet engine. It's a really cool little single-place engine, single-seat jet-powered aircraft. And wingspans about maybe 15 feet. Total length is maybe 18 feet. Really small little guy. You can see the engine on the back. It's a little turbojet engine. So we can take this baseline vehicle that already exists, it's already been flown, and modify the turbojet engine on it to include a turbojet engine, and it might look something like this. So here's our spaceplane version of this subsonic aircraft. We're obviously going to have to add a couple additional things. We'll need some tankage to carry the oxidizer. Those can be external tanks. The wing is more than sufficiently strong to carry that. The vehicle is not designed to fly above supersonic velocities. Its airspeed is V&E is about 300 knots. So if it goes supersonic, it'll need some way to trim out the control at supersonic velocities. There's ways to do that. I'm showing some little canards. There's other ways to do that. You might need some sort of ballistic coefficient device, such as a streamer or maybe a drag chute to control yourself if you're re-entering and you want to control that a little bit better. And then you'll have to modify the engine on this with an integrated turborocket engine. So this system, I mean, it's not going to have a high delta V, but you should be able to get well above the Kármán line of 100 kilometers and maybe thousands of feet a second. Probably not 10,000 feet a second, but somewhere between 3,000 to 8,000 feet a second delta V. The engine uses on that vehicle is the Velkovitéš PDS 100 turbojet. This is a Czech-built little turbojet engine. It's about 20 inches long and about 10 inches in diameter. And this engine can be you can integrate a turborocket engine, which is shown on the right-hand side. That's a picture of a small turborocket engine that would fit in the hub space of the Velkovitéš engine. We typically say that the turborocket engine will generate about 5 to 10 times the thrust of the turbojet that it might be integrated in. So the Velkovitéš generates about, I think it's about 250 pounds of thrust. So the Turborocket engine that could be integrated in that engine would be between 1,200 and 2,500 pounds of thrust. The Turborocket engine could generate that much thrust that would still fit within this engine. If that makes sense. Okay, let's look at another conceptual space plane. This is one of my favorite aircraft. It's not as well known. It's a French aircraft known as the Fuga Magister. It was a training aircraft developed by the French in the 50s, and it's a very excellent aircraft. It was actually a glider, designed as a glider. So it has a very long wingspan, and it also has a relatively low ballistic coefficient, which makes it nice for reentry kind of issues. It has hard points for weapons, so that's kind of handy. You can mount machine guns in the nose, but we would take those out. It's jet powered, and it has two engines on that system that we'll go into in a moment. So to make this into a space plane, again, we would have similar kind of systems, external oxidizer tanks carried on hard points, a supersonic trim, and modifications to its engines that would integrate a Turborocket engine. The Fuga Magister uses the Marlboro series of turbojet engines developed by the French company that was the predecessor to Snecma. There's a few varieties. This one uses the Marlboro 4 turbojet engine. It's kind of a picture of it shown here. The engine is about, it's about 400 pounds, and it's about, it's about 3 feet long, 3.5 feet long, and it's kind of a fat boy because it has a radial compressor. So it's, probably 2.5 feet diameter or something like that. On the exit cone, you can integrate a Turborocket engine in that system quite easily without interrupting any of the turbojet elements of it. Okay, then the last system we'll look at, this is kind of probably one of the cooler ones, and that is the F-5 space plane. The F-5 Freedom Fighter, you could modify this one as well to make it quite a dandy space plane. Because it can operate at supersonic speeds, you don't need the supersonic trim modifications that you need on the other aircraft. And you can modify the GE J85 afterburning turbojets to accept the Turborocket engine to give it some pretty outstanding performance. It's designed for large external drop tanks, which can be used for the oxidizer. So those are some concepts for that. The GE J85 afterburning version, which is the -21 version, can also be integrated, again, with a Turborocket engine sitting into the aft space of the turbine hub, kind of right here. I hope that makes sense. That's the sizing constraint on the Turborocket integrated with an existing turbojet engine. Okay, so to summarize what kind of performance you could potentially get out of these systems, the subsonics aircraft, the Fuga Magister, and the F-5, the first column is the empty weight of those vehicles. That's just no passengers, no mass, just the dry weight of the vehicle. Second column is the MIGTOW. No, that's not MIG going their own way. That's maximum gross takeoff weight. Fully fueled vehicle. How much propellant you can put in there. You can see those respective numbers. So the difference between those two is the propellant load that you can carry. 500 pounds of the subsonic is about max you can do. Fuga can do about a ton. And the F-5 has an extraordinary 16,000 pounds of propellant load, and it's maxed out in the MIGTOW. So if you use our delta V equation that we showed back on slide 6, there'll be a quiz at the end, so be prepared to take that quiz. Just kidding. If we use that delta V equation and we plug in an effective ISP, which is an effective, I mean, sort of mission averaged, so average over the air-breathing portion and the rocket portion of, say, 500 pounds per seconds per pound mass, of 500 seconds, then that's the delta V that you could achieve with these vehicles. So the subsonics, you could get an extraordinary 11,000 feet a second. Fuga Magister not as much, 6,400 feet a second. And the F-5, an astounding 17,000 feet a second of delta V is achievable with that system. And when I say, when I use the term 500 seconds ISP effective, that's an integrated value that takes into account drag and ascent issues that are knockdowns on the performance of the vehicle. So these are not unrealistic numbers that you could theoretically achieve with these vehicles. Again, the turbojet thrust powers are given there. The subsonic's 290 pounds of thrust. Two of the matches here, the two Marlboro engines, each put down about 800 pounds and change. And then the two afterburning J85s on the F5 that produce about 5,000 pounds of aspirated thrust each. And with a multiplier of 7 times the Turborocket thrust against the turbojet thrust, you can see what those things are. So that's kind of a snapshot of what you could achieve for these conceptual home-built spaceplanes. Now, some might claim that an F5 with modified J85 afterburning engines hardly qualifies as a home-built turbojet engine, but I disagree. And I say that for the enthusiastic home builder, nothing is impossible. Okay. Now we're wrapping up here. We're getting close to the end. So, as I mentioned, if there's something that you can take away from this presentation, it might be this. Why do we even need home-built space engines? Why should we care? Why does it matter? Well, I articulated these 5 bullets. They're fun. That's a good reason to do a lot of things. It might provide freedom in the sense of, you know, flying through the air with Turborocket ease, maybe some transportations at high speed, maybe some interesting things you could do. Maybe there's a wealth creation that is a positive creation of wealth for everybody. It'd be quite adventurous, no doubt. And the challenge of it, the intellectual and conceptual challenge. And so I leave you with the quotation that if you understand, I don't need to explain anything. If you don't understand, no explanation is possible. So, again, why do we need space planes? Why do we care? Again, a few bullet charts. These are meandering more into the political narratives. But in a world of increasing globalism and centralization of power, space access is going to become much more controlled. And you know, our political masters and their proxies are going to carve that access out for them, and not for us, and we're going to be left behind. And it may become constrained to the point where, like any totalitarian regime, the extrapolation is the totalitarian regime is that which is, if it is not forbidden, then it is compulsory. And so we don't want to get into a situation like that. And maybe space planes may be a way for us to transcend that, and for the individual to experience space flight and personal liberty. Why? Well, a couple of logistical reasons here. There's a lot of runways in the world. There's tens of thousands of runways in the world. There are not 10,000 vertical launch complexes. The ascent trajectory in a space plane is relatively non-aggressive. It doesn't have to look all weird. It looks like a normal airplane kind of thing, and not a ballistic missile coming in. It's highly controllable, and it can be kind of stealthy, meaning that you don't have to get in someone's knickers to fly on a sit trajectory or some sort of nice, pleasant trajectory. And because it's plane-based, it's easier to integrate into existing air traffic control systems, which is going to be, from a bureaucratic entanglement kind of standpoint, I think, to the good. One last thing I'd like to leave you with, and that is this. So we've talked about some advanced propulsion systems here, rocket engines, turborocket engines, things like that. The future, who knows what it holds for advanced propulsion systems. I'm not saying anti-gravity. Not saying it. But advanced propulsion systems that may come along, by Gemini, you're still going to need the spaceplane systems. You're still going to need a place to sit. You're still going to need an E-class system. You're going to need all the systems that a normal spaceplane has. So even if you come up with an anti-gravity system, you can put it in one of these spaceplanes because you're going to need all that stuff anyway. So those are all to the good. Joe, you have a question.
Could you elaborate on stealthy on your ascent trajectory?
I cannot. Oh, no, I will not. No, I'm kidding. I can either, Joe, I can neither confirm nor deny that that would actually be possible, even though it's shown in my future. No, I'm kidding. Stealthy. I will elaborate on that. Stealthy. Well, in a typical aircraft, when you're flying along, you carry a transponder. And we all know this is why. You carry a radar transponder, and it sends out a blip, radio signal that air traffic control and see. So they know where you are. Why do you need a transponder? It's because they can't always see you in the radar systems, even with a metal plane, that has good reflectivity. If you're a small guy like one of these, you might not be seen as easily. And so, we want to obey the rules. We want to be team players. We don't want to antagonize our benevolent overlords. Our protectors. We want to interface with them in a positive way, and so even if we have, even if we can't be seen easily in a trajectory that we're flying along, we'll still want to have a transponder and be visible if we need to be. But sometimes transponders break and the switch gets jiggy, and things like that happen, and you go off the radar screen until you can reestablish contact. So maybe that's what I mean. Maybe I mean something else. I'm not sure. Yes.
Great presentation. This probably harks back to your previous presentation. Is there any need for the nozzles on the turbojet, on the Turborocket portion, to be variable in pitch?
Yes. Well, it's not necessary, but it's an important attribute. And thank you for mentioning that, Greg. I didn't kind of want to go into that on a great deal of detail, but the control of that beta angle, that angle of the nozzle, is actually how you throttle the engine. Because by changing that beta angle, you're not just changing the thrust component, you're doing that as well, but you're also changing the power balance of the system. Because as you change that beta angle, you're changing the magnitude of the tangential component, which is the source of all the shaft power. So that's how that works. And in this model, I actually show, this actually has variable nozzles on it. You can't kind of see it there, and I took the little cover off so you can kind of see it. But there's a linkage in there that you can drive an actuator to and fro, mainly fro, some to, and change the nozzle, and it'll change the beta angle on these nozzles as it's rotating. That was a design technology.
Thanks.
I have a question.
Oh, did you want me to stop, or did you?
Oh, no, I have a question.
Yes.
Yeah, I noticed that one has it looks like it has 3 of those nozzles on there.
Yes.
So is that the optimal for it, or is it just for that particular application?
Well, that's a great question, Tim. So the number of nozzles is a design parameter in the Turborocket engine. And the way it works is that if you add more nozzles, then you effectively shorten the aspect ratio of the nozzle. And this is a typical traditional rocket engine technique to reduce the length of the chamber nozzle on a rocket engine system. Because if you had one big nozzle, if you had a single nozzle with a given area ratio, and the area ratio is defined as the exit area divided by the throat area. If you just had one, it's kind of long, say of a given length. But if you chop that nozzle into, say, 4 nozzles or 3 nozzles, that have, now the throat area is the throat area original of 1 divided by 3, same with the exit area, it's that exit area now divided by 3, distributed among the three nozzles. Now the aspect ratio remains the same, but the nozzles become shorter. And so that's something that's an important design parameter. You kind of need sort of short nozzles on a rotating system like this. So having multiple nozzles helps you. It's sort of in the turbo machinery world, it's kind of a rough rule of thumb that you usually have an odd number of blades or nozzles. And the reason for that is that you want to avoid a 1 per vibration excitation. If you have pairs, if you have an even number, then you can get this half pi over 2 excitation on the dynamics of the system. And so we typically like to break that up with an odd number of blades, turbine blades or compressor blades, and in this case nozzles as well. But that's not a hard and fast rule. But I like to use 3 or 2. or 9 or 7.
You mean like a resonance frequency?
Yes, it's the dynamics. It's the dynamics of a rotating system,
All right.
which I describe in great length in my book, I might say, and in chapter. There is some discussion on it. Okay, so I'm getting near the end here, and let's wrap it up here. Okay, we've had some ideas, we've had some concepts. What should we do next? Well, there's some ways you can get involved. There's some ways that you can move towards your own, realizing your own home-built space plane, and at least moving the community that way. And so here's a few things you can think about. And I would say start with designing and flying your own designs in a simulation environment. And a really good one, I think, is X-Plane. If you've ever played with X-Plane, it's sort of a, it's more than a game. It's really a simulation environment. You can design and build planes. It has accommodation for different propulsion systems like rockets and turbojets. It's very easy to use. The software costs $70. So look out.
It's nothing compared to the aircraft we're buying, right?
Yes, the simulation environment, unlike other software development programs, is negligible compared to the hardware. And then so you can design your own systems, play around with performance, fly them exo-atmospherically, do a lot of fun stuff. That'd be a great place to start for low cost, only investment of your time. The next thing I would say was, support the Turborocket engine design and development. That could be, follow our Turborocket design and development on our YouTube channel and the web page. Design and build your own Turborocket engine system. That would be a great way to do that. And and if you found a book on the subject, you could buy a book on it on Amazon. So then move into existing and modified aircraft like some of the ones I've shown. And then if you have untapped millions that is burning a hole in your proverbial pocket, then you can design, build, and fly your own spaceship prototype. Pull together a team and let it rip. Okay. So if you'd like to learn more about home-built space planes and turbo-rocket engines and things of that nature, I have a YouTube channel, Turborocket. Just go to YouTube and search for Turborocket, and you'll see that channel and the associated videos. If you like and subscribe, that really does help me. I mean, I know that's kind of, you hear that so many times, like and subscribe, but it really does help move the Turborocket channel to a chance where it may be able to be monetized, and that'll help the Turborocket engine development. If you really want to go deep, there's a book on the subject. It's available on Amazon, and that will fulfill your deepest Turborocket engine development needs, I believe. Here's my contact information. If you want to contact me, you can see it there. And in closing, I'd like to say that I thank Tim and the HAL 5 Society for making it possible for me to give this presentation. Tim has been courteous enough to record the video, and he'll make it available on the HAL 5 site. I usually make a little video on the Turborocket site that links to that, so you can go watch that video, or send the link to a friend, to friends to encourage the development here. That helps our development here. But so in summary, I thank you for your time and your interest. I hope you find this topic and this presentation interesting, and that there were some ideas that you had that were engendered here that might be inspiring, might catalyze some of your own thoughts on propulsion, home-built aerospace planes and space vehicles, and that those ideas can be realized together as we develop these interesting technologies. Thank you very much. Okay, well, we have a few questions. First, we're okay on time as far as I'm concerned. I'm delighted that I could talk for such a great length of time, and you guys hung in there with me, so thank you for that. Great, yeah.
I have to run, 2 words or possibly one? Space drone.
Space what?
Drone.
Space drone, yes. Well, space drone, yes. Well, you need to talk to Mr. Berkmans, because he has some great ideas on that, and so we have the outer mold line, OML, by the way, outer mold line, sorry. That's one of those TLAs, 3-letter acronyms. used it there. So that, the outer mold line is developing on that system and has some interesting propulsion systems for that. So, so those are some of the ideas there.
Cool.
Yeah, space from, good idea. Other questions? Mr. John, yes.
It's not a question, but more of a comment, and that is that you might mention that the concept of conventional aircraft flying to space has already been demonstrated with the NF-104 aircraft.
Yes.
I don't know if you want to just maybe describe the NF-104 a little bit, like how amazing that was.
Yeah, thank you, John, for mentioning that. Yes, so there actually there was a rich history of advanced space planing and rocket-powered aircraft, of which the NF-104 is one of those. Basically, the NF-104 is basically the F-104 starfighter, probably one of the coolest looking airplanes that ever emerged from the Cold War. You know, it's this very pointy-looking thing, man with a missile, it was sometimes called. So that baseline F-104 starfighter vehicle was fitted with a rather powerful hypervolute bipropellant rocket engine in the tail of that, and it was flown very much like some of the trajectories we were talking about here. You know, we'd fly up to altitude, supersonic speeds, ignite the rocket, and then climb out. Chuck Yeager in The Right Stuff, I just saw the movie. That was the engine that he entered a flat spin in and got injured and stuff, and that was flight testing with that vehicle. But that's a good example of the F-104, the rocket-powered vehicle. There are others. Well, I mean, obviously, the Bell X-1 rocket-powered airplane, carrier aircraft on a drop ship, which was a World War II era bomber. And then all of the series of the X-planes, you know, fall into that category. You know, hardly home-built space planes, but certainly the precursor technology to these systems. And you know, we build upon the past, and we have existence proofs of those types of vehicles were viable and doable. And you know, if you've ever been to an experimental aircraft, Oshkosh, Airventure, and see the technology that these home builders have created and put together, it's astounding. And so, you know, if you've never believed that home-built space plane might be possible, go to Oshkosh and you will believe, because it's an extraordinary event. Questions? Yes.
A little bit, I reuse the word bothered by the idea of putting a sufficiently powerful engine on my Cessna 150 that it can go orbit. Now, am I going to fly the edge of what the airframe can stand because of the air density as I go up? Is that how I get to orbit?
Well, so if you, well, I would answer it in two ways. The first answer, I would say that, no offense, that sounds like a pretty stupid configuration, put a rocket on a Cessna 150. Yeah. So that seems like a poor choice of flight vehicle and propulsion system.
It's that ballistic coefficient that I'm worried about.
Well, so that's the kind of downside of it. You know, the going upside might be something different. So we quantify the dynamic forces on flight vehicles in the atmosphere, typically using the term the dynamic pressure. And the dynamic pressure is just you know 1/2 rho v squared, and it's just a term that we use to kind of get a sense for the magnitude of the aerodynamic forces on a vehicle. And so typically in a flight vehicle, you fly very prescribed flight corridors to minimize or to optimize the dynamic conditions of the flight vehicle. Cessna 152, its flight corridor has been optimized and designed for, you know, under 20,000 feet and under 130 knots. What, do you know what VNE for?
If that fast.
So I don't know. I don't remember what VNE velocity never exceed for a 152 is. I think it's around 130, 140 knots. So that wouldn't be a good choice for that. But I would also look at it this way: if you had a magic propulsion system that could propel your vehicle, your Cessna 152, at a steady velocity. That's just a standard flight. That's just a standard trajectory kind of process, right? What if the vehicle never exceeded 100 knots at any condition, and you had your magic propulsion system? Then you could go to arbitrarily high altitudes. So it's not the vehicle. It's not the vehicle that constrains it. It's the dynamic forces that it encounters. So if you had a spacesuit and climbed into 172 and you had this magic propulsion system that could fly at arbitrary altitudes, and you maintained 100 knots, you could go arbitrarily high, right? I mean, there's nothing to prevent you from that. And then as you re-entered, and you stayed at 100 knots, you're still fine, right? So it's not the, I say all that to say it's not the vehicle, it's how you fly it. So now, the example vehicles I'm giving here, you wouldn't necessarily be able to take those up to orbital velocities, and I make no claims there. What I wanted to show you, and I hope your takeaway from that picture, from that slide, is that for reasonable propellant fractions and these propulsion systems in the vehicle weight, these are the theoretical delta V's that you could achieve. And that's kind of the punchline from that. But you make a good point, and I think I'm hearing what you're saying. Yeah. Yeah.
So John, you didn't address fuel type. Typically in a turbojet, they run in what, JP4, JP7, something like that, kerosene.
Yeah.
Is that what you're going to use for the Turborocket portion of your design as well, so that you don't have to carry multiple fuel types in addition to your oxidizer?
Yes, that's a great question, Dave. Thank you for bringing that up. So, yeah, propellant choice is an important design parameter for space vehicles in general and space planes in particular. If you're a bipropellant rocket engine, you're going to need an oxidizer and fuel. And so you're going to need to carry those, and what are those going to be? If you're a turbojet engine, you're an air breather, you're going to be operating some, like you said, kerosene-based fuel, a Jet A or one of the JPs, and so being able to use the JP as the fuel, and then some other oxidizer as the oxidizer, like liquid oxygen or nitrous oxide. That will be an important design parameter for your system. And thanks, Joe. Thanks, David. Appreciate that. That will be up to the designer to do that. I think it's possible that you could use the Jet A for the air breathing engine part, and then you could have a different fuel like methane, liquid methane, or one of the other hydrocarbons. And liquid oxygen, for example. But if you can use a kerosene and a Jet A in conjunction with the fuel that you need for the turbojet, that's a synergistic benefit, and I think it would be desirable to do that as you can, as long as you don't compromise the performance of the system. I like kerosene and Jet A hydrocarbons. I think those are good fuels. My oxidizer of choice, I tend to like liquid oxygen. Liquid oxygen, you get a little scared because it's cryogenic, it's very cold. But there's some real advantages of liquid oxygen. First, it's very dense. It's a very good oxidizer, one of the best. And it's ubiquitous, So pretty much any place where you have atmosphere, which is pretty much any place on the Earth, and pretty much any place where you have electricity, which is pretty much any place on the Earth, you can make your oxidizer, you can make liquid oxygen. And it's extraordinarily cheap. Last time I looked, liquid oxygen runs around, 5 or 6 cents a pound. It's just cheaper than milk, certainly now. And so it's a low-cost, high-density, high-performing oxidizer. And if you want to get rid of it, you just dump it on the ground and it vaporizes and it goes back into the atmosphere. So it's easy to get rid of, easy to make. high performance and low cost. So if you can get over the difficulties of the cryogenic fluid management, which we have one of the world experts
I
here.
was going to talk about CFM.
So if you have that, then
If you have product questions, I can answer them. Yeah.
so we know we can handle that because we have world experts.
But I actually did have a real question, though.
Okay. Did that answer your question, Peter? Okay. No, your question.
Yeah, I've been thinking about propellant choice also. And is there any real drive to have the two propellants for rocket mode be of like density? Because I was looking at your equations, and chamber pressure is proportional directly to density of the liquid that you're trying to spin up,
Yes.
right?
Mm-hmm.
Remember that from your previous discussion?
Yes.
And so it occurs to me that if you had two propellants that were of very different density, say hydrogen, liquid hydrogen and liquid oxygen, that might prove some kind of challenge, right? Or no?
Yes, it does. So
Wait, is there a book on that?
So if you look on chapter 4, I go through the sets of equations necessary to solve the bipropellant turborocket engine solution. And you're exactly correct. And this was one of the great technical challenges that I ran into when I was trying to put together the computational methodology for computing turborocket engine performance. What happens if you have, and what Noah's getting at is, you have this spinning rocket spinning around, okay? The propellant flows in, it flows out to the edge of the engine, in a little thing there, and so as it's flowing out here from the rotation, the pressure that it achieves is a linear function of the density of the fluid. So if you have a really high density for
It's just rho GH, right?
it's rho G. It's 1/2 rho G. It's 1/2 the isodynamic pressure. The pressure that you get here from the rotation is equal to 1/2 rho U squared, where U is the rotational velocity. So yes, it's a linear function of.
I was thinking about it like a hydrostatic pressure in a way.
Yes, that's a good way to do it. That's a good way to think about it. Chapter 4.
Or like V squared over R equals acceleration, kind of.
Yeah.
That's what I was trying to.
Yeah, it's the standard hydrodynamic hydrostatic pressure in a rotating cylinder. It's a chapter. It's slide 16 in the previous slide. Anyway, that pressure there from each fluid is a function of the density. So if you have a high density fluid of the oxidizer and a low density of the fuel, there could be a pressure mismatch. And the way that is accommodated is that the pressure drop across the injector solves that.
So are you forced to choke off the oxidizer in that?
No. The system will set up a dynamic equilibrium operating condition in which the dynamic conditions achieved by the system from the tangential component of the jet velocity, it's the power supply, pumping those two propellants into the chamber. But you can't control the mixture ratio. Without controlling the orifices. You have to set the orifice sizes in order to get the appropriate pressure drop so that they both arrive at the chamber.
I guess that's what I meant about choking the oxidizer off. You have to constrict it at the injector plate in order to get the right mixture ratio.
Well, so you either constrain the mixture ratio and have to set the orifice sizes, or for a given set of orifice sizes, the mixture ratio is an output variable. It is one of the solid variables.
You don't want to do that though. The impulse just gets creamed when you do that.
You can set the orifices such that you get the appropriate mixture ratio. This is a kind of a long technical discussion, and
we'll do that later.
It's pretty detailed, but I can say that the solution methodology that I provided in the book, I'll just summarize it this way, provides a way to compute the performance of a bipropellant engine. And so I've identified the sets of equations that you need to solve that. And basically, there are 11 equations. So 11 equations, 11 unknowns. You solve that set of equations, and that gives you the design point operation of a bipropellant to a rocket engine system, in which all the pressure drops and the resulting mixture ratio are computed as a solution to that set of equations. So that's, I'll just say that as a personal summary.
It's a jetting problem.
What's that?
It's a jetting problem.
It's a jetting problem, but it's tractable. It's tractable.
Can you show that slide again?
Which one?
The one that you said was number 16 that showed that.
Oh, that's in the other presentation. I guess I could pull that up,
No.
but I have to switch slides. I'm sorry, Robin. I think I've gone too far. Sorry about that, Robin. You look disappointed. I'll try to. I'll see what I can do in just a minute. Okay. Other questions?
Yeah, I have a question. Instead of hydrogen as a fuel, what about methane or natural gas?
Yeah. So I personally like the middle hydrocarbons. Noah and I have actually spent some time together, working on hydrocarbon fuels and their virtues for rocket propulsion engine systems. And so you kind of turned me on to a number of the middle hydrocarbons, butanes, and even pentane had some virtues. I kind of like methane. It's kind of the
worst one.
It's kind of the worst and the best. I mean, it's kind of it has a better density than hydrogen, but not as much ISP. So there's some, and it's inexpensive too.
Yeah.
Because it's available in very large.
Now, methane is liquid. It's not quite the same range, but it can be liquid at the same temperature as liquid oxygen, right?
Yes.
So that
Not at atmospheric pressure, locks will freeze it.
locks.
Well, but there is an
Pressurize it.
There is a range. It's on your chart there.
Yeah, you have to pressurize it a little bit. You get it to about 50 psi or so.
So there is a range where the liquid oxygen won't freeze the methane.
But at atmospheric it will.
Okay.
Oh, yes. Another one is propane. Propane won't be frozen by it.
It's the only hydrocarbon that locks doesn't freeze.
Yeah, it just makes it kind of unique. And it's also fun. It's a good camping fuel, and it's reasonably dense.
Yeah.
It's not as inexpensive as methane, but it's not bad.
Yeah.
I've tested it in Turborocket Engine.
And it's Hank Hill approved.
What's that?
It's Hank Hill approved.
Okay. Yeah, right. Okay. That's from the TV show King of the Road.
King of the Hill.
Cartoon show that sells propane. Yeah, pretty sweet. So.
And propane accessories.
And propane accessories, yes. You may need that for your cabin or not. Other questions? Yeah, don't let. So these vehicles can achieve high delta V's. I'm not saying they can go all the way to orbit on a single stage. I'm not saying SSTO. I'm not saying that. We use the term. We use the shibboleth, the code word, if you will. We use the term high delta V missions, so that kind of keeps people from losing their potatoes when they think that your delta V is too high.
Do you recall the delta V requirement for SSTO?
Well, so a typical orbital velocity requirement, and it kind of varies, is about, I think the number is about 25,000 feet a second.
That's what I would.
That's about what I would use. So 9,000 meters a second is another number. You can actually, at lower altitudes, you can actually get below that, below 25,000 feet a second. Even as low as 22,000 feet a second at low altitudes, and be in orbit, but it's kind of a high drag environment and stuff like that. That may be a good place for space planes. I don't know. So that's kind of the number. So not that far off. So a vehicle that can take off without in a single stage and make orbital velocity without staging is kind of the holy grail. It hasn't been possible yet, though there are people that did the calculations, for example, on the S4B Saturn stage. That vehicle, that stage, which was the second stage of the Saturn V, that vehicle had a dry mass fraction and a corresponding propellant fraction that it could theoretically make orbit with just that single stage.
Just got enough thrust to weight, though.
It was never tested with that. I thought it did have enough thrust to weight.
Isn't that one J2?
It's 5 J2.
Oh, that's the 1.5, that's right, I'm sorry.
So that one, the numbers showed that it could make single stage orbit. I don't know if it ever could. It was never tested that. And there's some other vehicles that have been.
So you're talking about the S2 stage?
Yes. Yeah. And there were some other ones that were pretty close as well. But it hasn't been shown. It's never been flown now.
Aren't the Chinese launching their space station with a single stage?
I don't.
Taking the first stage all the way to orbit?
Yeah, well, they're making it pretty high, but for the one that they launched like 9 months ago?
I don't think so. Now, maybe a parallel burn where they have boosters that fall up, and you can't make
It wouldn't really
a single stage with a single massive stage. Yeah.
It was close.
Okay. So.
Yeah, it's 7:30. We're gonna have to start closing up
How's your
now.
power doing, by the way?
It's low, but it managed to go on one charge.
Okay.
One
Well,
full
very good.
charge.
Well, thank you very much for your great questions and for coming tonight. I very much appreciate it. Thank you for supporting these ideas. I hope it was stimulating to you, and I hope you come away from this presentation feeling more hopeful about our aerospace future. Thank you.